Hi everyone. My name is Sakthidasan Kalidasan, and I'm a graduate student at the University of Utah. Very excited, nervous, and grateful to be here. This is my first in-person presentation, and yeah, happy to be here to talk about my research. And yeah, I'll be talking about energy and accuracy characterization of the burst mode real sensing approach for smart contact lenses. Without further ado, let me jump into my talk. So the motivation behind the work we do, like presbyopia is a common visual disorder which affects roughly 1 billion people worldwide, and just North America alone, it's like 100 million. And the current solutions like bifocal lenses, they are good, but in terms of robustness, they can be significantly improved. And our collaborators at the University of Utah, they conceptualized this idea of smart contact lenses, where you potentially combine a range sensor along with a tunable lens, and you use that as an alternative approach to treat presbyopia. So in today's presentation, I'll be focusing only on the range sensing aspect of the system, and I'll talk about the energy requirements and because this is a wireless system, so energy is kind of critical, and I'll talk about how we can empirically decide what is the right energy requirement for implementing this approach. So before going deep into the presentation, let me give a basic idea about how we are using this range sensing approach. The fundamental idea is kind of simple. So when you have two coils, the coupling coefficient between the two coils are a function of the angles between them, and using this, we can kind of estimate the angle between the coils if we can measure the coupling coefficient. So how do we measure this coupling coefficient? We transmit a signal in one coil and just receive at the other coil, and based on the received amplitude, we kind of estimate what is the coupling coefficient. Now, why is this useful? This idea, when you mount this coil on potentially on an eyeball, but for other purpose, we are using a mock eyeball. When you mount this, and if you're able to kind of get what are the angles between the coils, using basic trigonometry, you can estimate the range of the object the eyes are trying to focus on. And this is at the heart of what we are trying to do here. And in order to decouple, if you see the equation for range, it has both theta L and theta N. Unfortunately, coupling coefficient is a function of both theta L, theta R, and we want to decouple them. So in order to do that, we use we get two signals instead of just having one coil at the receiver. We have two coils. We get one signal VA and one signal VB at the receiver. And because both the inner coil and outer coil have different orientation, physical orientation, we get different signals. And using these signals, we can kind of distinguish theta and theta. And we use a calibration-based approach for implementing this range sensing function, and which is like we store the function of VA and VB versus the angles as a lookup table to minimize the complexity of implementing this. And so quickly, background information about the work we have done in the past. In previous work, we showed proof of concept, but for this range sensing approach, but we use like unrealistic input signals, like 20 volt peak to peak, which you don't want on your eye, right? And burst mode. So we also realized that we cannot send continuous wave signals into this, and it's highly energy inefficient. And we needed some kind of burst mode approach. We proposed that approach. We theorized kind of theoretical estimation, but we didn't know what exactly was the relation between how many signals you're sending in burst mode and the accuracy of the measure. This is one of the main goals of the work I'm presenting today, which is like understanding accuracy versus energy trade-offs in the measurements, and also improving overall power efficiency with respect to our previous design, whatever we. So earlier we just hooked up, PCB, sorry, coaxial cables to the coils, and we didn't use any electronics. And that was a main problem with respect to why we are getting so bad. We need 20 volts peak to peak signals and things like that. So we went in and used some off-the-shelf components to design a transmitter and receiver in order to improve the power efficiency of the system. So we have a buffer in the transmitter. What it does is just improves the power transfer between the signal generator and the transmitter coil. And we also, because we are isolating the cable capacitance out of the coil resonance, we are able to push the resonant frequency to 20 megahertz. And also we use a LNA at the receiver so that we can have smaller transmitted signals at the transmitter. That's it. These are the main reasons we are using this electronics, for our characterization. And just a quick overview of what we mean by reverse mode approach. It's quite straightforward. We have square wave signals, and we just send pulses of any cycles, into the transmitter, and we just observe the envelope at the receiver, and we measure the amplitude once it settles, based on the received signal. And why we use envelope is because there is some inherent averaging present in the envelope detection, and that helps to get a better signal at the receiver. Yeah, so this is the test setup we use to perform the experiments in characterization. And so we have signal generator, and we use the transmitter, PCB circuit and receiver PCB circuit. They are mounted on a motorized, system, which will, kind of turn as in order to get the measurements for different combinations of angles. And we use a PC for post processing for envelope detection, things like that, and also to control the system, the angles and whatnot. So we don't show it here, but right now they are using a Faraday cage to reject the ambient noise. And this is this. And okay, so here, so earlier I mentioned we use a lookup table-based approach for range sensing mechanism. And so why exactly we use a range sensing calibration plot? So the idea is to minimize the number of times here. If you can just measure once in a day, very good quality receiver VA and VP with respect to the angles, we can store it in a lookup table, and we don't have to worry about the analytical relationship between VA, theta L, and theta R. Given that we are able to calibrate the system on a daily basis, and that the frequency can be changed. And we use like a 1 volt peak to peak signal, like over a long period of time, something like 750 cycles to generate these plots. And from this, these two plots, we inverse map it to the range, and we get this nice plot which says like for this VA and this VB, your estimated detector range is somewhere in this plot. This is not a good plot, but it's actually nice if you can look at it in a three-dimensional mode. So how is this helping us? In order to reduce the energy requirements for the range sensing approach. So when you perform burst mode, that is the measurements which happens at a frequency of like once every second. You don't have to really generate really wait for 750 cycles and generate very high quality measurements. You can actually give some reduce the number of cycles you take to perform each measurement. And of course, you are going to lose some accuracy, but that is what we are trying to understand. Like, how do we know what for some level of target accuracy, what is the minimum required number of cycles you have to send in the transmitter. And you can see this is an example of the measurements we measured in the lab for 30 cycles. And This is the low noise plots, and this is like for just 30 cycles. And even though you can see, of course, there are noise in the system and the measurements, but still the overall shape is kind of kept intact. This just demonstrates that there is an opportunity to minimize the energy requirements of this range sensing approach. So this plot here kind of sums up most of the information I want to I measured in the lab and I want to convey here. Like if you can generate empirically, if you can generate for different input parameters, what is the change in accuracy, which is we measured it empirically because it's very difficult to analytically calculate all these things. So when we have a plot like this, we can go in and say, if we require something like 95% accuracy, then maybe you should use like an input signal of 0.75 volts and 30 cycles, and something like this. So we don't know if 95% is the right accuracy. It could be 99, it could be 90. We don't know at this point. But if we have this information, we could readily go in and say, what is the right number of cycles and right input voltage to get this range sensing function to at least the target level of accuracy. So we demonstrated this range sensing approach using off-the-shelf components, and it consumes like 180 nanowatts of average power per measurement. But we think that with a custom ASIC, this power consumption can be reduced significantly, because right now we are using off-the-shelf components which are optimized for ultra-low noise, and if you can relax those noise constraints, when we design a custom ASIC, this average power can be significantly reduced. And with that, I would like to summarize today's talk. And we successfully demonstrated a functioning range sensor approach, which operates in burst mode, and also we demonstrated the relationship between accuracy and energy requirements of the approach. And we predict that when we implement, we did some MATLAB estimations, and we kind of guess at this point we're guessing, but we are hoping that when we implement it using a custom ASIC with just 1.6 nanojoules per measurement, we will be able to implement this range sensing. And in future work, we are hoping to perform a more comprehensive characterization of this accuracy versus energy requirements, because right now we are doing envelope detection in MATLAB, and we are using a Faraday cage to get rid of the ambient noise. We would like to include the filtering and the averaging on the board and see how much it adds to the energy requirement. We are also pursuing a custom ASIC design for enabling this as a wireless implementation, and these are some of the references I used for the talk. And thank you for listening. And